Alright gang, so here we are for chapter 3. We're going to be talking about the epically amazing molecule that is water and why water is so important to biology and to life as we know it. So let's go ahead and get started. Just a quick little overview of chapter 3 here. It talks about how water is a molecule that supports all of life as far as we know it. If there is life on any other planet, if it exists in any form similar to the life that's found on Earth, it's going to require water. Water is the biological medium for all of the processes that occur for life here on Earth. So if we find living creatures elsewhere, we expect that that's going to have to include water. Water is a substance required most by living creatures. You yourself could probably go without food for quite a number of days, but you couldn't last without water more than perhaps 2 or 3 days at a time. Most of your body's made up of water. Most of your cells are made up of water. You're probably about, as far as mass, your body's about 70 to 75% water. And the cells themselves, depending on the kind of cell, is anywhere from 70 to 95% water. And of course, it's water that is the main reason, a primary reason that Earth is habitable. And most scientists would say that life began in a solution in the ocean in water form. So if life is so important to the creatures here on Earth, for example, it doesn't matter if it's a killer whale in the ocean or this polar bear, what about other planets? A little bit later in the chapter, we talk about astrobiologists, and astrobiologists are the ones who might work for NASA or other space organizations that are looking for life on other planets. And inevitably, whenever we're looking for life on other planets, they're searching for water because we know that it's necessary for the type of life that lives here on Earth. So where could water be possibly in our solar system? Say just looking within our local neighborhood here. Well, oftentimes they're searching for Mars or water on Mars. Right now we have numerous robots cruising around on Mars. We have the Curiosity rover, the largest one at the moment. And then, of course, we had Spirit and Opportunity, one of which is still working. And they're looking for evidence. And there seems to be plenty of evidence that there was, at one time, large amounts of water on Mars. There does seem to be ice still on Mars underneath the surface, and perhaps, maybe, even liquid water in certain cases, but we haven't really found a lot of evidence of that. So perhaps a lot of scientists seem to think that the conditions on Mars were more favorable for liquid water and potentially life in some form, perhaps millions to billions of years ago. How about currently? Well, the picture down here on the screen is of one of the moons of Jupiter called Europa. And Europa is a fascinating object. This picture, if you blow it up, it's even more fascinating, but it's basically an ice-covered ball, and the outer surface of Europa is a giant ice sheet, and most scientists think that beneath this ice sheet is perhaps liquid water in some form. You can see these cracks in the surface. They're indicative of liquid water welling up between the cracks in the ice. So perhaps because of its condition and location, and the tidal forces that pull on this moon Europa by Jupiter, there could be enough thermal energy underneath that ice, within that water, to allow for living creatures to exist. Now, they could be microbes, they could be something else. We, of course, don't know, but Europa is constantly one of the sites that NASA and scientists and sometimes the general public are very interested in. It would be amazing to go and perhaps somehow drill a hole down through this ice and see what's below. Just like we've done with the other chapters, we're going to divide this into a few concepts. I think this chapter has maybe 3 concepts, and we're going to start with concept 3.1. Polar covalent bonds in water molecules result in hydrogen bonding. You may have been thinking, my goodness, I thought we were already done with chemistry, but apparently not. So some of the chemistry that we discussed in chapter 2 has a lot to do with water and why water is so unique. The water molecule is held together by polar covalent bonds between the hydrogen and the oxygen. We already discussed how the oxygen is kind of like a big sister, kind of tends to steal or bogart some of the electrons. And so most of those electrons that are shared between the hydrogen and the oxygen, they tend to accumulate or stay around the oxygen more. That means we have polar areas on this molecule where the molecule in general is neutral as far as charges. It is not quite neutral all around in all different places. So the oxygen molecule would have more of a negative charge, and the oxygen atom would have more of a negative charge, and the hydrogen atom area would have more of a positive charge. This is an animation. Of course, it won't play in this view, But if you look at the PowerPoint slide, or I think even if you look at the PDF file, you can get this animation to play. And I've also put this animation on the website underneath the notes area. So here we have another version of this, and it shows how there is bonds between the negative and positive portions of these different water molecules. So if the oxygen has a slightly negative charge, it will be attracted to the slightly positive charge of the hydrogen right here. And you can see the same thing occurring right here. Also on the website, I put a link to a TED Ed video that you might want to take a look at. It's down here listed at the bottom. You can look at it in lesson format, or I think on the website I just put the YouTube link. This is not required. You don't have to do a particular assignment like you did the last time, but this would just be for more information if you wanted to see it in another format. Here we have another configuration, just another way of drawing it. We had the 3D view, and here's more of a line drawing view. So if you looked at this configuration of these two water molecules, you might want to ask yourself, why would this configuration be unlikely? And if you can't answer that, you might want to go back and take another look at some of the notes or the chemistry notes that we've talked about so far in Chapter 2 and thus far. But why would this configuration of these two molecules be somewhat unlikely to occur? We're going to go ahead and get to Concept 3.2, and then we'll take a break. Concept 3.2 talks about these 4 emergent properties of water. And water is a pretty amazing substance, and these are 4 properties of it that make it so that it's so biologically important, and so that it contributes to this sustainability of life here on Earth. So the 4 properties that we're going to take a look at, one of them is cohesive behavior, cohesion. One of them is the ability to moderate temperature. One of them is the expansion upon freezing. And then the 4th one is the versatility of water as a solvent. So we'll quickly take a look at all 4 of these. The first one is the cohesion of water molecules. So within these water molecules, we have hydrogen bonds that form between these molecules. So like we said, you have slightly negative areas on the oxygen atom, slightly positive areas on the hydrogen atom area, and they bond together. So the water molecules basically stick to each other, and this is called cohesion. Cohesion is when like materials stick together. So one water molecule sticking to another water molecule is cohesion. And cohesion is what allows for the transport of water up a very tall tree. For example, how does that water get from the roots down there in the ground all the way to the top of a 20, 30, 40, 50-foot tree? Well, cohesion helps. We're going to watch a video on that in just a second. The second term that's related to this is adhesion. And adhesion is also an attraction, but it's the attraction between different substances. So, for example, the attraction between water and the plant cell walls, or the attraction between water and the side of your glass, that's adhesion. So cohesion is when the water molecules stick to each other. Adhesion is when the water molecules stick to something else. Here we have a quick little animation. Again, you can't see it in this view, but if you check it out in the PDF or in the PowerPoint notes, you can see an animation of how cohesion and adhesion help a tree take water from the ground all the way up to the leaves. And I highly encourage you to go into the materials, go into the notes, and look for the BioFlix movie. It's called Water Transport in Plants. I placed it in the Chapter 3 notes folder. These BioFlix movies are amazing animations. They're really good. Really nice animations, far better than this little animation that you see right here, as a matter of fact. So go into your notes and look for the BioFlix movie, Water Transport in Plants. Again, it's in the Chapter 3 notes folder, and it'll show you how adhesion and cohesion help this entire process. So one more picture here. This shows a nice microscope view of the 2 types of water conducting cells. You have xylem and phloem in the plant there, and you have these conducting channels, and you have water molecules as the evaporation occurs, or actually it's transpiration. As a transpiration occurs out the leaves, those water molecules that are becoming gas, they tug on each other. And because of this hydrogen bonding, that would be the cohesion, and the adhesion to the sides of the wall of the plant, you have this motion all the way from the ground, like an unbroken chain, all the way up through the top and out the leaves. So as these molecules transpire or evaporate and leave the plant, they tug on the entire chain, and this entire chain of water molecules gets pulled to the top. Here's another view of those water conducting cells. Other places you can see this cohesion of water molecules is in surface tension. Surface tension is basically a measure of how hard it is to break this cohesive layer, this cohesion of the molecules on the surface. And you see this pretty easily if you go out and you drop some water on your dad or mom's freshly waxed car. You see how the surface tension and the cohesion allows these water droplets to form, these nice round droplets. And you see in this picture right here, where if you're very careful, you can take an object such as a paper clip and you can actually set it on top of this surface layer. And if you do it carefully enough and you don't break the surface tension, it'll rest on top. And that's because you have this cohesive layer of water molecules, and those hydrogen bonds are difficult to break. And this object isn't heavy enough, the gravity doesn't pull on it enough to break those bonds. Some living creatures even take advantage of this. Here you have a spider. There's even some creatures as large as a type of lizard, a basilisk lizard, sometimes called, nicknamed the Jesus lizard, because it has the ability to run across the surface of the water. Now, if it were to stand in place, it's too large and gravity would pull it and the surface tension would break. But here you have various bugs like a spider, water striders, who can actually rest on the surface of this water surface tension and not break through those hydrogen bonds. The second emergent property of water we're going to look at is the moderation of temperature by water. So water has a couple of properties that relate to temperature and thermal energy. One of those is that water absorbs heat from warmer air and then releases that stored heat to cooler air, and that water can absorb or release large amounts of heat and not change its own temperature very much at all. For example, if you lived in a coastal area, like we're looking at the west coast here, coastal areas tend to be quite a bit more moderate in temperature due to their proximity to the ocean. In other words, they don't cool off as much at night, and they don't heat up as much during the day as if you go inland. So here you can see just the difference in, say, 40 or 50 miles from the coast, where the heat of the day rises quite a bit in Palm Springs, San Bernardino, and it doesn't get nearly as hot in the coastal areas. And that's because of the huge mass of water, of course the ocean right beside them. So when we're talking about this emergent property, we need to make sure that we define some terms: heat and temperature. You're probably familiar with energy, potential energy, kinetic energy. Kinetic energy is the energy of moving objects. That could be the energy of a baseball flying through the air, or it could be the energy of air molecules moving around in a gas form. So kinetic energy is the energy of motion. When we talk about this word heat, the key word here is heat is a measure of the total amount of kinetic energy. Sometimes I've seen heat and thermal energy kind of talked about the same way. So heat or thermal energy. The key here is that is the total amount of kinetic energy due to molecular motion. So this involves the amount of mass that we're talking about. Temperature is the other phrase. Temperature is a measure of the average kinetic energy of the molecules, and that does not necessarily involve the mass. So just to show you what the difference is, we have a massive iceberg, say the size of your house or the size of a school on the left, and we have a cup of coffee on the right. Now you would definitely say the temperature of the coffee is higher than the temperature of the iceberg. The coffee might be close to boiling, where the iceberg obviously is close to the freezing level of water. But if we looked at the amount of heat or the amount complete total thermal energy, the iceberg would still be higher. So you might say the amount of heat is higher in the iceberg than it is in the cup of coffee, but the temperature of the coffee is quite a bit higher. Have to excuse my pop-up message there to give my dogs their medicine. All right, so back to where we were. So the iceberg may have a total amount of heat or thermal energy that is greater just because it's so much more massive, but the cup of coffee has a higher temperature. Another way to think about that would be to ask if you had to make the choice between having a thimbleful of boiling water poured on your hand or a gallon of boiling water poured on your hand, which one would you take? And obviously you choose the thimbleful of boiling water, even though both of those would be the same, 100 degrees Celsius or 212 degrees Fahrenheit. Both of those are the same average kinetic energy temperature-wise, but you know the gallon of boiling water contains a lot more heat, a lot more thermal energy, and thus it would do greater damage than the thimbleful would. Other terms to know involve some of the measurements that we use. Of course, in science we use the metric system. All countries use the metric system in their daily life, except for three. Those would be Liberia, Myanmar, and the United States of America. But we always use the metric system when we're talking about science. That way we can share our work with scientists from around the world. So the Celsius scale is used for temperature. That's measured in degrees Celsius. A calorie is an important term. That's the amount of heat, the amount of thermal energy required to raise the temperature of 1 gram of water by 1 degree Celsius. Now don't confuse that with the calorie that you see on a food package. That's actually a kilocalorie. So on the food package, if it says 1 calorie, that's actually the equivalent to 1,000 of the calories that we're talking about here. So 1 calorie on a food package would raise the temperature of 1 gram of water by 1,000 degrees Celsius, or it would raise 1,000 grams of water 1 degree Celsius. So on a food package, that calorie is actually a kilocalorie. And then the last one we talk about is a joule. A joule is a measurement of energy. If you've taken IPC or physics or something related to that, you've probably studied joules. And a joule is equal to 0.239 calories, or 1 calorie is equal to 4.184 joules. Now in my class I would never ask you to memorize these formulas, because I would always expect that you would have access to a formula chart of some kind. So don't worry necessarily about memorizing formulas or conversions, just at least kind of have an understanding of what these measurements are. One of the reasons water is so good at moderating temperature is because it has what we call high specific heat. Specific heat is the amount of a substance, is the amount of heat that can be absorbed before that substance will raise its own temperature. So for example, again, we're talking about 1 gram by 1 degree Celsius. So the specific heat of water is 1 calorie per gram per degree Celsius. So it will take in 1 calorie before it will raise its temperature by 1 degree, if we're talking 1 gram of that material. If I grab a chart really quick here, let's see if I can throw in a chart and show you some examples. Go right here. This is in joules instead of calories, but remember a joule is equivalent to 4.184 calories. So just as a quick comparison here, move this around just a little bit, we can see where water has a specific heat of 4.184 joules, and remember that's equivalent to 1 calorie, and you can compare that to some other materials. So what we're saying here is that water will absorb this amount of heat, this amount of energy, before it changes 1 degree Celsius. So if we're comparing 1 gram of all of these materials, look how much energy water will absorb before it changes 1 degree Celsius. Compare that to ice, compare that to lead, granite, copper. So if you wanted to change the temperature of 1 gram of copper, you do not have to input a very large amount of energy, of thermal energy, to do that. Whereas water, you have to input an enormous amount compared to, say, something like copper. So water resists changing its temperature because it has a high specific heat. That's why, for example, we use it as part of the cooling system for an automobile. It can absorb a lot of the heat from the engine before its own temperature starts to rise. Or, if you'll notice, if you go to the beach on a hot day, the asphalt of the parking lot or the sand, they get hot way before the water gets warm. And so even though the water, the sand, and the asphalt have been out in the 95-degree sun all day long, the water can absorb a lot of that energy and heat before its temperature starts to rise. So why is that? Why is water so unique in this particular capacity or ability? Well, it goes back to that hydrogen bonding. Because those water molecules are hydrogen bonded to each other, some of that heat, some of that energy is absorbed before those hydrogen bonds break. And so before the water molecules themselves can even start to move around, remember, moving around is kinetic energy, and that's what we're measuring when we measure temperature. Before those water molecules can start to move around and speed up themselves, those hydrogen bonds have to be broken. So a lot of the energy that's inputted into the water molecules goes to breaking those hydrogen bonds before it ever starts giving them greater kinetic energy. So the high specific heat of water minimizes temperature fluctuations in and around that water, and that's very good. That means that water environments are more stable. Their temperature doesn't rise and fall quite as much, and it's not as big of a swing when it does rise and fall. And again, going back to just if you live in a coastal area, you see a good example of that. So if you live along the coast, you don't have as wild of temperature swings. And that was probably very important to the beginnings of life on our planet. Most scientists would say that the evidence shows that life began in the oceans or in the water. And that's partially probably because it allowed for greater amounts of chemistry, but it also allowed for conditions that were not as harsh or conditions that were more stable. And if you're going to have life begin and then grow and evolve, you're going to have some stability within the environment. Another beneficial aspect of water is its ability to provide for evaporative cooling. Evaporation, of course, is when you're going from a liquid to a gas, and specific heat was the amount of thermal energy that was required to raise the temperature of a substance 1 degree Celsius. Well, here we have another term that's somewhat similar. It's called the heat of vaporization, and that's the amount of heat or thermal energy a liquid must absorb for 1 gram of that liquid to be converted to a gas. And as the liquids evaporate, it is providing cooling because it's taking some of that energy with it. So, for example, when you sweat on a hot day, that sweat, as that liquid evaporates and leaves your skin, those water molecules that have become a gas, they're taking that amount of energy with them. So they're leaving behind cooler water molecules. So they're taking energy from your skin, and that provides the cooling that you feel. So not only humans have this ability, lots of other creatures use this evaporative cooling to help regulate their temperature. And so then you might want to ask yourself, if you were to compare a 90-degree day in Houston, Texas to a 90-degree day in Las Vegas, Nevada, which do you think would feel better or worse, and why would that be? A third trait of water we're going to look at here is the fact that the solid version floats on the liquid version. The solid version of water is less dense than the liquid version, and that's pretty weird when you think about it, because almost everything that we study in chemistry, almost everything on the periodic table, elements or including compounds, molecules, when they're in their liquid form, they are less dense than in their solid form. In other words, the solid version of gold, if you take a solid piece of gold and you drop it into a container of liquid gold, the solid gold will sink toward the bottom. It is more dense. But here we have the opposite. We have ice, the solid form, actually floating in the water, being less dense than the liquid version. And the reason for that is, again, going back to these hydrogen bonds. Water acts just like any other material as you start to cool it. It actually becomes more and more dense. So water that is warm water, like in a bathtub, is less dense than cold water that you get out of the refrigerator. So it increases in density as the temperature drops, but only to a certain point. Once it reaches about 4 degrees Celsius, that's where it's at its greatest density. And as you drop to 0 degrees Celsius, to the freezing point, what happens is there's not enough energy for those water molecules to break those hydrogen bonds and move around and rub up against each other as much. So what happens is the amount of energy is lost, and those hydrogen bonds actually hold the molecules apart and hold them in a particular crystalline structure. And so when they freeze, they're slightly more apart. The distance between those molecules is greater than when they're in the liquid form. And of course, that makes it less dense. This is a good thing, because if ice sank, water would be a very different substance, and life on Earth would probably not be possible. If you can imagine, here in Texas, it doesn't happen very often, but if you lived up north, if you can imagine, every time a pond or a lake froze over, that water would fall down toward the bottom. It would freeze and sink, and then freeze and sink, freeze and sink. By the time winter was over, you would have nothing but solid ice from the very top down to the very bottom. So even in the oceans, in the Arctic oceans or freshwater lakes, this ability for ice to float, here on the left, you see how that crystalline structure forms because of hydrogen bonds, and how the molecules are actually more separated from each other. On the right, you see how they have enough energy to break and reform those bonds constantly, and so the molecules are actually a little bit closer together and more dense. So here you have a little shrimp. He benefits from that fact that ice freezes, floats on top, actually helps to insulate the water below. So during the cold winter, say in the Arctic oceans, the water below the ice actually stays at a higher temperature because it's insulated from the outside air. and that allows all these creatures to exist. If water sank to the bottom, obviously we wouldn't have that ability. Slowly over time, you would have nothing but frozen ice sinking to the bottom and filling the lake or the pond. The last trait of water we're going to look at before we take a break is that water is called the universal solvent, the solvent of life. A couple of terms you're probably familiar with. A solution is a liquid that is a homogeneous or homogeneous mixture of substances. You have a solvent, which is what does the dissolving. Generally, we're talking about aqueous solutions, which means water is the solvent. And then you have the solute. The solute is the material that's being dissolved. So a solution is a mixture of a solvent and a solute. And water turns out to be one of the best solvents around. So water is such a versatile solvent because it is a polar material, because it has these areas that are positively charged and negatively charged. And so if you have ionic compounds or other polar compounds, they can be surrounded by water molecules in what's called a hydration shell, and that allows for them to be dissolved and go into a solution. So here's a good picture of salt. Remember, salt is NaCl, and it's an ionic bond. Remember, the sodium gives away its extra electron to the chlorine. So the chlorine is negatively charged ion, and that's an anion, and the sodium is a positively charged cation. You can see what happens. The negative chlorine is surrounded by the more positive hydrogen parts of the water molecules, where the positive sodium here is surrounded by the more negative oxygen side of the water molecule. So it doesn't matter if the ion is positive or negative, water can surround it. And here you have the clump of salt, the crystals of salt, being slowly broken away and then hydrated by the water surrounding it. So water can dissolve compounds made of polar molecules. Maybe they're not ionic like salt is, but as long as they have some positive and negative portions or sides, they can be dissolved. Even if they're pretty large molecules like proteins, which are generally fairly large, they can be dissolved in water as long as they have either ionic or polar regions to them. So for example, here we have a water-soluble protein. That big purple molecule is huge compared to the small water molecules. But again, as long as there are some negative and positive portions, you can have hydration occur, and that entire molecule can be surrounded by water, and it would be what we would call dissolved or hydrated. So materials that have an attraction toward water or an affinity toward water are called hydrophilic. So hydrophilic substances are generally easily dissolved, not always, but they have an attraction toward water because they're either polar or ionic. The opposite of that is hydrophobic, which would be like a fear of water. Hydrophobic is a substance that's not dissolved by water. It doesn't have an affinity toward water. Like, for example, in your salad dressing, if you mix oil and vinegar is a water-based material, or oil and water, you'll notice that they don't mix well because the oil molecules are basically non-polar. They don't really have positive and negative edges and sides, so they're hydrophobic. Sometimes you can get a colloid. A colloid is a suspension of small particles in the liquid. So we wouldn't really call that solution. The particles are not fully dissolved, but they're suspended, and that would be a colloid. That would be somewhat similar to a solution, but where the particles are not completely dissolved. When we're talking about aqueous solutions and chemistry, the concentration of the solute makes a big difference because for chemical reactions to occur, we have to have molecules bump into each other. So if you have a larger amount of solute in the solution, you're going to have greater activity. You're going to have a greater amount of chemical reactivity. So just like the picture down here shows, the low concentrations means you don't have as many molecules running into each other. A higher concentration means more collisions. So the amount of solute, the concentration of the solute does make a difference as far as the reactivity. And another example, like a totally unrelated example, would be if you were to compare the number of car wrecks that occurred every year in Dallas, say in the year 2013, and compare that to the number of car wrecks that occurred in Dallas in 1923. Well, which one would you expect, 2013 or 1923, had more car wrecks? And what type of trend would you expect to see if you compared the years from 1923 to 2013? And why would you expect to see that trend? And it's pretty obvious. In 1923, obviously there weren't that many cars in Dallas, Texas, so there probably weren't that many collisions. But in 2013, there are hundreds, thousands of cars, so you would expect, because of that higher concentration, there's probably more wrecks, more accidents. Chemistry works the same way. A bit more chemistry here before we finish up. Because when we're talking about atoms and molecules, we're talking about huge numbers of these materials. We usually use what we call moles. So let's talk a little bit about molecular mass first. Molecular mass is the sum of all the masses of the atoms in a molecule. So for example, if we're talking about water, which is H2O, we have 2 hydrogens and 1 oxygen atom. Now if we look on the periodic table, we can find the mass of each of these particular elements in Daltons, or sometimes we talk about atomic mass units, AMU. So hydrogen has 1 and oxygen 16. So if we add 2 hydrogens and 1 oxygen, we would get a molecular mass, which is the mass of the complete molecule of water, of 18. We're rounding that off, but we're going to just go with our rounded off number of 18 Daltons, or 18 AMU. Now, the mole is a unit of measurement, much like, say, a dozen, where a dozen stands for 12. Well, a mole is a much larger number, 6.02 times 10 to the 23rd. And because we're talking about such small pieces, when we talk about molecules, we're usually talking about large numbers like that. So that number is called Avogadro's number, named after a scientist, Avogadro. In science, whenever you do something cool and you're fairly famous, after you die, we usually name something after you, name a unit after you. So 6.02 times 10 to the 23rd is called Avogadro's number. And the way that the Dalton was defined was that 6.02 times 10 to the 23rd Daltons is equal to 1 gram. So if we wanted to know the exact number of molecules, say, in a material, it's difficult to measure the number of molecules, but it's easy to measure the mass in grams. So if we take the molecular mass of water, which is rounded off 18, and we have 18 grams, there goes another pop-up. If we have 18 grams of water, that will be the equivalent of 6.02 times 10 to the 23rd molecules. So a mole is a unit of measurement, and it indicates a certain number of molecules. And using the molecular mass, we can get that into grams. So for water, 18 grams will give us 6.02 times 10 to the 23rd molecules of that material. So 6.02 times 10 to the 23rd, that's the number of water molecules that are in 18 grams of water. And then we have this unit called, this measurement called molarity, or this unit, it is a unit. The molarity is the number of moles per liter of solution. So when you're dealing in chemistry with acids and bases, and they talk about a 1 molar solution or a 0.5 molar solution, that's the number of moles of the solute, whatever that is dissolved, per liter of solution. So these are just ways of measuring and describing when it would be very hard to actually use numbers of molecules, because the numbers would be so large. Finally, just to wrap up this part here, again, talking about the possible evolution of life on other planets, it's difficult for us to say whether or not there's life on other planets, because we don't have any evidence to support that. We don't know how common life is in the universe. We're always searching for those types of answers. But we do know if there is going to be life on other planets like we find here on Earth, it's going to require water, because all the life on our planet requires water. So that's generally what astrobiologists are seeking. Is first they have to find planets, then they have to try to find water on those planets, and that may lead to the possibility of life. Using NASA's Kepler telescope, Kepler mission, we have found a huge number of planets, exoplanets outside of our solar system, probably well over 200 by now. The Kepler mission seems to be doing an amazing job of identifying planets. Many of these are not within what we call the Goldilocks zone, which is an area that is close enough to their star but not too far away to have liquid water. If you're too close, like Mercury or Venus, you tend to be too hot and all your water has evaporated and is not in a liquid form. And if you're too far away, say someplace like Neptune or Pluto, then you don't have the ability to have liquid water because it's way too cold. So we're looking for planets that fall within this Goldilocks zone that have liquid water. and potentially that could be a place where perhaps life could develop. We'll end this section with this cool shot showing some morning frost on Mars. Some of our rovers have been doing some amazing work up there on Mars, and so here's some evidence of water underneath the surface, frost underneath the surface. On Mars itself, it's a combination of water, H2O, the water that we think about forming ice, as well as dry ice, which would be solid carbon dioxide. So here you have some frost on the morning dirt sample scraped up by one of the Martian rovers. And again, where there's water, well, potentially there's a greater chance there could be or could have been life, and that's what they're searching for. All right, we'll take a break, guys. Come back and we'll continue.